Okay, so in this video, I'm going to be going through the first lesson I posted on here for week 3, um, called the constant E. And it's something that I meant to post last week and didn't have enough time for. As you can tell, I'm from probably reading this that I'm getting a little bit behind, but I'm trying to get back to a normal pace. Anyway, so I'm going to go into this. And this is my walkthrough, so if you don't, feel free to pause the video. I'll have a little pause screen up every so often just for fun, but also just to let you know like when I want you to think about a question on your own and pause the video and then come back after. So first off, I want to know just where are you at today? Like, how's everything going? It's week 3 of distance learning. We've got 8 or 9 more weeks of this, and hopefully we can make it through. Doing the best we can. I'm curious. So for me personally, I'm kind of on the tired side, but I'm feeling pretty positive. So I'll put myself somewhere around here. And let's see what else could I say about this? I'm still getting used to things. To this distance learning. Um, it's a little rough. Okay, so just let me know where you're at, and then move on to this next screen. So in this next screen, we're going to start this lesson. It's called, what is the constant E? And who is this dude? So this is Jacob Bernoulli. He discovered the constant E in 1683 by studying a question about compound interest. So he said, what if we had an account that had $1 in it and it paid 100% interest? At the end of the year, it would have $2 because 100% means we're going to double it. We're going to match what's there. But what happened if we compounded it more than once during the year? So, for example, if we wanted to do it, kind of have 2 payments during the year, then we could split it up and maybe do 50 cents and then another 50 cents or something like that. What would it be like? So in this lesson, we're going to walk through the same ideas that he kind of thought about to discover this constant that we now know as the letter E. And it's a really, really fascinating constant. It's one of the highest of importance, of the highest importance in mathematics, alongside other constants such as pi. If you any fans of pi out there, 3.14159. We'll talk more about pi in the next unit, hopefully before this year is out. And I is another really important constant, which we learned about this year. It's the imaginary number. So these are some really, really important constants in mathematics, and so is this constant E. Maybe pause for a minute and think, what questions do you have, or what do you wonder about this constant? I'll put on my first pause screen and take a minute and let me know what you think. Okay, so hopefully you wrote some kind of question about it here, or maybe even it's just like, who is what's up with this dude's hair? But hopefully you had maybe some thoughts like, what the heck are we been learning about? I'll go on to the next screen here. So here we're going to look at the compound interest formula, right? Because Bernoulli here, he's thinking about compound interest, and so let's remember first what even is this compound interest formula. So here's the formula that we kind of talked about last time. P is this principal amount. It's kind of like what we're starting with. Times 1 plus R, where R is some interest rate, some percentage change that we're increasing by, to the power of t, where t is the number of times that we're multiplying by this rate, or number of times that we're compounding. So let's read this. So let's suppose Allegra, who is an undergraduate student, opens a student loan account to pay for her college expenses, and when she graduates, she owes a balance of $38,650, um, which is actually the average student loan debt in Connecticut from a couple of years ago. Pretty close to we have just so you know, we are the highest in the country of all the states for student loan debt for our graduates. But anyway, this is our average student loan debt, $38,650. I'm gonna have to move myself here. Let's see, I'm gonna put myself over here. Perfect. So using this formula, let's fill in the table for her student loan amount. If she makes no payments, that the loan companies aren't going to be happy about that. They'll probably charge some penalty fees, but let's not take that into consideration. If she makes no payments and her loan here just continues to increase at this rate of 4.8% per year, which is the average federal student loan rate. So what does this mean? Well, she's going to start with, principal amount, which is $38,650. Gonna put here. And what will it be after 1 year? Well, after 1 year, I'll just start this off and then I'll pause the video in a second. She will owe $638,650 times, we can kind of plug into this formula here, 1 plus 4.8%, which is 0.048 to the power of 1. So in the past, we might have just written this as 1.048, but this is kind of just clearly indicating that it's an increase of 4.8%. So she will owe, after 1 year, $40,505.20. So as you can see, the loan companies, the people who give out these student loans are making money by doing this. It's to their benefit because they are charging interest each year, and so that amount will increase. So why don't you take a moment, and fill in the rest of this table, and come back, and we'll compare notes. Okay, so hopefully you've tried to do this on your own, but let's go through it. I mean, we're just plugging into this formula, right? So after 2 years, we're going to have the same exact thing, except it's going to have increased twice by this rate. It's a little hard to see, but it's to the power of 2. So her student loan she will now owe $42,449, and let's round this to 45 cents. All right. How much will she owe after, year 3? Well, we're just going to do this again, but now we're going to put it to the power of 3, and, you can see how this thing is slowly increasing. As we saw from, looking at this sort of exponential growth before, these changes will be small at first, but then later on, kind of in the last few years, it will increase quite a bit. That's the nature of exponential growth. Let's keep filling this in. So to the 4th, how much will she owe? 46,622 cents. 5 years in, she'll owe $48,860.28. So 5 years later, she owes, an extra $10,000 a pop over what she originally borrowed from the loan company to pay for her college expenses, tuition and whatever. And so that's a lot of money, $10,000. Hopefully she has a pretty good job after college. After she goes in. What about after 10 years? How much will she owe after 10 years? Ooh, now we're up to 61,000. $767. And 10 years is a um, standard length of time for a student loan. But they also offer things that are called extended loans, and you can pay it off after 15 years. But then you can see here, you are letting this grow quite a bit. $78,000. That's, I think, is that double? It's about double what she originally borrowed. Okay, so it's just a little bit of calculation first here. Might be a little bit, might be quite a lot of calculations in this lesson. But thankfully, I think because I'm not finished with the other one, so this might be the only lesson for this week. Let's go on to the next page. So, monthly interest. In reality, the student loans and other financial accounts, savings accounts, they don't accrue interest every year at the end of the year, like in this case. They're not saying, okay, we're going to tack on 4.8% of what you owe us now at the end of the year. They're going to actually try to do that every month, right? So that's kind of that's how the world works. Everything's monthly, and of course they want their payments each month too. So how does this work when we try to break it down into a monthly increase over time? Well, here's what they do to make it simple. They're not going to kill you here. They're not going to make 4.8%. They're not going to make it grow by 4.8% every month, but they'll take that 4.8% that it's supposed to grow over the year and say just easily divide it by 12, and say, okay, we'll increase it by 0.4% each month. How much will her student loan be after each month now? So here now we're looking at months from 0 to 12. And you don't have to fill in all of these. Maybe I'll skip around a few. But how much will it be at the end of the year now? Is it going to be the same amount as before? Let's see, after 1 year, she owed 40,505. Is it going to be the same amount? I mean, we're just taking the same interest rate and dividing it by 12. But we're doing that each month. What do you think? So let's see. First, she's going to have our original amount. Nothing's changed. And then 1 month later, we're going to increase it by 0.4%, which is that. So let's see. We'll have 38,650 times 1 plus 0.4% is 0.04. So this is 0.04%. After 1 month, she now owes $38,804. Maybe I'll just start rounding to dollars. Make it simple. Okay, and if we keep doing this now, each month she's increasing by this 0.4%, which is a smaller increase, but she's going to do it 12 times in the year. Pause the video and see if you can fill in the rest of this table and see what is it going to be at the end of the year after 12 months. Okay, so let's come back to this. And feel free to take a break, please. If I say like pause the video, don't go through this all at once. It is kind of a long lesson. Feel free to take breaks. That's why I'm posting this stuff on YouTube in a video form. So let's go through this stuff. So this is after 1 month. She's increasing by 0.4%. But after 2 months, well, she's going to do the same thing at this smaller increase, but now it's going to happen twice. So she'll have, 38,959. And then let's kind of skip around. Let's go to 5. After 5 months, almost halfway through the year, how much will she now owe? 39,009. Okay, so it's growing. It's growing even more slowly because we're looking at each month in particular. What if we skip down to like 11 months? Now she owes $40,385. And after 12 months, finally, at the end of the year, she owes $40,546. So this is what I wanted to compare to the previous amount. So she's paying monthly now, and she owes 40,546. How does that compare to what the year was before? Before she owed 40,505. 505, 546. So this is a little bit more. So it does, what's happened here? It's actually changed how much she'll owe by the end of the year, even though all we did was say, just take her annual interest rate, her annual growth rate, and divide it by 12. Why is it any different? Well, if you remember, the way that compounding works is that interest is kind of being added onto itself. So if after 1 month, they grow this amount that she owes by a little bit, then the next month it's going to grow even more. It's going to get compounded even more so. So she's going to owe. It looks like she's owing about $40 more. 505, yeah, about $40 more by the end of the year. Not much, but a little bit. So let me see. Let me say here, she will owe about $40 more than before. As you might have guessed, let's see. Okay, we're going to the next screen here. The formula for compound interest when this compounding happens more frequently during the year looks something like this. So it's kind of like what we just did. You take your interest rate and divide it by how many kind of like increments throughout the year that you want it to get compounded, or divide the interest up to. And then in 1 year, it's going to happen that many times. So if it was each month, then we take the interest rate and divide it by 12, but then we do this 12 times in 1 year. So hopefully this makes some sense. If you feel free to take your time with this formula. But that's basically what's going on. So we did this for month by month before, for up to 1 year. Now let's kind of like take it out to 10, 15 years. Let's suppose Allegro's student loan has interest that compounds each month, which is totally realistic, much more realistic than once a year. This means n equals 12 in the new formula. So how much will she owe after each year? Well, her principal amount isn't changing, 0. After, initially it's $38,650. But now after 1 year, how could we figure this out? Well, we can plug into this formula again, but n now is equal to 12 because it's happening 12 times in 1 year. We're going to break her 4.8% up into 12. So let me write this out. So $38,650 times 1 plus, it was a 4.8%, so it was 0.048. Now we're dividing that by 12. And we're going to raise this to the 12 times in 1 year. So let's see here. So after 1 year, we get that 40,546 that we got before. 40,546. What happens as we go out throughout the years? Why don't I pause this and see if you can fill this in, and then we'll compare it to what we had on screen 3 when we looked at all the years going out, but with this new formula. Okay, so, well, we're really, again, just plugging into this new formula for compound interest that happens in smaller increments throughout the year. So we're going to kind of do this same thing that we had here. Now we're going to do this 12 times in 1 year times 2 years. So what this says is that it's going to happen 24 times in 2 years, right? It's happening every month, 12 times a year. After 2 years, it's 24 times. I'm just going to leave this like it is. And we say, look, you've got 42,536. I should have had a chart. Side by side after this. Okay, and we can keep going. Let's skip down to maybe 5. We'll compare this. So 12 times a year for 5 years. Now she's going to owe 49,110. And I can go back and kind of compare that to what we had before. After 5 years, happening once a year, she owed 48,000. Now happening monthly after 5 years, it's 49,000. It's a couple $100 more. What about after 10 and 15 years? 12 times a year times 10 years. Now she owes after 10 years 62,401. And after 15 years, 79,289. So what's going on here? How does this compare? 75,289. Wait, that's not right. 78,000. Did I do this right? Oh, that was 79. Whoops. 79,000. So before it was 78,000. Now it's 79,000. In other words, because of this compounding every month, she owes an extra $1,000 because of the small amount of incremental kind of like interest building on interest that happens from switching to monthly. Okay, let's see. Okay, what happens now? Here's the formula again. Just to get some more practice here, you know what? I'll take this slide out in the actual the one that I send out to you guys. I don't need you to go through and do this all again. What I was going to do is say, what happens if what happens if it gets compounded each day? Like if we narrow that time frame, and n became 365 now. Well, you might maybe instead I'll get rid of this table and I'll say, what do you think's going to happen to the amount that she owes? Take a minute and just reflect, and then come back when you've got an answer there. Okay, so let's see. I'm not going to fill in this table. I'll get rid of the table. But what do you think is going to happen if we move from once a year to every month, right? Happening 12 times a year, to every day, happening 365 times a year, right? What do you think is going to happen? If you said that the interest, even though she's going to be paying a smaller amount each day, is going to compound even more on itself. If you said that her amount will be even larger, that's right. It will grow. It will be even larger than before. It was monthly. It was compounded each month because of this kind of like interest building on interest. The more frequently it happens, the more it's going to be able to grow on itself. I'm going to have a lot of weird hand signals in this video, and that's okay. Okay, so now let's go back to Bernoulli's question. He asked, what happens if interest is compounded if we took this to its ad infinitum furthest extreme. What if we compounded more and more and more frequently? Not just 365 times a year. What about 1,000 times a year? What about 10,000 times a year? What happens to the amount when you do this? Because of the compounding effect of it, because of this compounding effect, is it just going to blow up and become that amount that she owes, instead of being $60,000 or $70,000, would it become like 100,000, $1,000,000? What would happen? So he said, let's start with this simple example. Your account's going to start with $1, and we're going to assume a 100% interest rate for the year. So here we plug this into the formula, starting at $1, 1 plus 1, because this is 100%, happening once a year. What's the value of the account? Well, it's $2. You can plug this into like a calculator, but you get dollars, right? Because we're starting with $1. It's happening once a year. It's increasing by 100%. But then, what happens if we make it smaller? So we do it, instead of 100% one time, we'll do 10% 10 times. So that's what this expression is showing us. We're starting with $1, we're increasing by 10% here, but we're doing that 10 times. Nominally, this is like the same thing, right? But we know that when you compound more and more frequently, it has more time to grow on itself, the interest. So how much will you get? Well, we can kind of like plug this in to our thing here, and we said, oh wow, actually going from 1 time a year at the end of the year to 10 times a year, we get this big increase of, instead of $2, it's now $2.59. Gained a whole 59 cents on the dollar. Okay, let's do it even more. He wants to make a lot of money, right? Let's do it, instead of 10 times a year, let's do it 20 times a year. But we'll try to still be fair to everyone. We'll do it 20 times a year, but we'll only increase it 5% each time. How much does that come out to now? We can kind of like plug this in again. Say here's 5% increase 20 times. Oh, it's not as big of a jump, but we've gone up to $2.65. So it's, this jump was huge, from 2 to 2.59. Now we've gained another 6 cents. So it's not like it's blowing up like crazy. So let's kind of do this again and see what happens if we do this sort of ad infinitum. We'll just kind of do this again and again with more and more frequency, but smaller and smaller increments. Go ahead and see if you can write down the expression, and then figure out, and then put that in the calculator and see what you get as the value of the account. All right, hopefully you took a break, come back. Let's see, so what is this formula going to look like? Increasing by 1% 100 times. So, well, we're going to have 1 times 1 plus 0.01 to the power of 100, right? And let's kind of like just fill in the form. Oh, it tells us here what that is. 2.7. What about this one? Now we're increasing by 0.5%, by 0.5%, 200 times. We're going to have $1 times 1 plus 0.005, that's 0.5%, 200 times. Looks like this is going to become the calculation here, which is good, nice. So $2.71. Okay, so we've gone from $2 once a year, if we do this once a year, to $2.59 if we do it 10 times a year, 265, 270, 271. It looks like it's actually getting, like the increase is getting smaller, so maybe it's approaching some limit, right? Some amount. Let's keep going here. 1 plus 0.001, 1/10 of 1%, 1,000 times. 717, maybe I'll call that. Let me actually, even though I know you can't go past like a penny, let me write this value down, 2.717. We'll keep going. 1 times 1 plus 0.00. So if this would be 0.1%, we need another 0 in here. So a really, really, really tiny amount we're increasing it by. But now it's happening 10,000 times. Move myself again. We're increasing by this tiny amount 10,000 times, and we're getting closer. We've got 2.718 is this value that we're getting closer to. We can get even closer. 1 times 1 plus 0.00, a tenth of 1%. This would be another 0 and another 0. I think that's correct. 4 zeros. And it's happening 100,000 times. So increasing incrementally by a really, really tiny amount, 100,000 times. What do we get closer to? Oh, it looks like we've leveled off. We're not getting any bigger than this. So we get to this number. It looks like the value approaches, and when you take calculus, if you take calculus in a couple of years, you will actually do something like this. This is called, it's reaching a limit. It's getting closer and closer to a certain number. What that limit is 2.718. So that's really fascinating. It didn't blow up, even though, we said compounding and more and more frequently, kind of like interest will build on itself, but it doesn't, it reaches a finite amount, and that finite amount is 2.718. So this value, 2.718, is the constant E. It is the same mathematical constant that Bernoulli discovered, and I couldn't tell you why we call it E, just that's what we refer to it by. All the other letters, I guess, were taken. And it's what happens when you take this limit that we just did. If something that increments very, very, like by a tiny amount, almost you could say infinitely small amount, but infinitely often, it gets closer and closer to this number, 2.718. And so we call this continuous growth, because rather than something that's happening once a year or 10 times a year, it's happening at every single instant of time, infinitesimally, or instantaneously, I guess you could say. It's increasing by a tiny amount. So this is called continuous growth. That's what E is about. We get to this number every time we do this. And so a lot of natural processes in the world can be modeled with this constant. If you think about the growth of organisms, you are constantly growing from the time that you were born. You were constantly growing pretty much nonstop at every moment of time. There's some kind of changes happening. It's not like, you were 5 feet tall when you were 10 years old, and then you were 2 inches taller the next year. Like, it's not like you suddenly, what I'm saying is, it's not like it was your birthday, and that on your birthday every year, you grew by like an inch or half an inch or something like that, right? That's not how growth works. It happens slowly over time. So this e, this constant here, is used to model that kind of growth, because this is what we get to whenever you have something happens continuously over time. It's also used to model the decay of radioactive elements, or the diffusion of heat, almost everything in nature. Um, what else? What else do you wonder about E? It's a really interesting thing. Maybe, if you have any thoughts or you have any questions about it, I'm interested to see what you think or what you are curious about. And E, as if you study more mathematics, it will come up again and again and again. Is there anything I wonder about E? I guess I wonder if there are any other mathematical constants like E. Fancy here. Um, because I'm not sure. It's very unique. There's pi and there's I and there's E and there's not a whole lot else that I know of. Okay, so just kind of step back here a little bit. E is this crazy, irrational, transcendental number like pi. They're the only two transcendental numbers. I'm not going to explain what that means. They're the only two that we know about. I mean, there's a few others, but they're basically all combinations of those two. And it's very interesting conceptually, this idea of like instantaneous growth, instantaneous continuous change. But in reality, but when it comes down to it, it's just a number, right? It's 2.718 dot dot dot. Just like pi is 3.14159, you could call it 3.14. So when working on problems involving E, we rely on calculators to kind of estimate its value. You don't want to be typing in 2.718 over and over and over again. So most calculators, almost every calculator, has a key on it. If you're using one of your own calculators or a graphing calculator or something like that from school, there's a key for it. I maybe I should show you. Let's see. Let's a graphing calculator. Let's take an image of a graphing calculator just so I can show you where it would be on one of these TI-84s. Kind of taking a side here. This is kind of more. Sometimes I like making the videos like this because it go on these asides like I would in class. Um, you know me. I tend to get off track, off topic. But let's see. So where is it? This is a really low res. This is a low res image. Let me pause it while I find one. So here's a TI-84 Plus CE. I think these are actually the ones Mr. Cohen uses in his class in statistics. And if we look down here, I'm going to zoom in. There's a key right here, e to the x. You might have wondered what this means, and now you know e is this number, this mathematical constant. So there you go. Now in Desmos, if we were going to like use this calculator up here, it knows what e is. So let me move myself here. So if I type in the letter E, it just knows, oh, that's 2.718. That is this constant. And I know it looks like it repeats, but it doesn't actually repeat. So Desmos knows what this is. We can plug in other numbers. So go ahead and plug in these numbers and see what their values are. Right? Let me pause it for a second. Plug those numbers in and see what you get. Okay, so let me type this in here. E to the 1.1 is about 3. So let me copy and paste that in here. Math equals to 3. Well, e to the 0.7. E to the 0.7. That looks like it's all about, we can call it close to 2. And last but not least, what is 24 times e to the minus pi? You know me. I'm going to put this kind of crazy stuff in here. E to the minus. Now, how do you type in pi? There's a key here for Desmos, just like there would be a key on your calculator. Or, because it's smart, it knows what e is, you can also just type in pi and it'll change it to pi. Letters pi. And look at that. It's close to 24 times e to the minus pi is close to 1. 3, 2, 1. Okay, so, it's just a number. Let's go on to the next screen here. So now we have 2 different models of growth, right? How can we use E to help us represent things in the world? We know kind of where it comes from, but how is it actually used? Well, let's compare it to our more familiar model of exponential growth. Suppose we had a population of 9,000 bacteria in a petri dish when it was first being studied, and we noticed it's growing by 2% every month. Using our previous model, we would say that this function represents how many bacteria there are going to be after t months. Right, we're starting with 9, and this is in thousands. 9, and we're going to increase it by 2%, 1.02, a certain number of times. Well, this formula is fine. It's exactly what we're asking about. This increases by 2% every month. It represents discrete growth, though, so it means that after, it's kind of it's showing that after each month we're going to increase by 2% monthly. Or we could use this model with e in it now. 9 times e to the 0.02 t. And this represents continuous growth by 2%. So the question is, how are these similar? How are these 2 models similar? Remember, this with e in it, that just means that it's happening at every instant of time. There's some small amount of growth. And I'm saying that these 2 models are pretty similar. Why don't you plug them in here using p and using the first one and using the second one for different lengths of time, t, and just compare them, see how close they are. I'm going to put up the pause screen and write some observations that you notice here. Okay, so let's go ahead and do this. You probably already have your numbers in here. I'm just going to give me a minute, please. Okay, so I'm going to take this model of discrete growth. Discrete meaning happens at certain intervals of time. Let's say we've got 6 months, about 10.1. About after 12 months, about 11.4. How about after? I know I've got so many tables in this lesson. I'm sorry. 24 months, growing 2% each month, 14.48, 4748. How about after 48 months? 23.28. And last but not least, after 100 months, 65.2. In thousands, 65,000. So, okay, so that's our original model, right? What about with this E? With this E craziness? Well, we're going to plug in the same kind of thing. 6. When we do this, we put in 6 months, we get 10.1. Okay, so looks about the same, right? How about after 12 months? 11.44. Yeah, I should have gone out another decimal place. Here we got 11.41. Here we got 11. Maybe I should do this here. 10.13, 10.14. Here we got 11.41. Here we've got 11.44. Okay. But with our E model after 24 months, 14.54. Still very, very close to what we had before and using this other model. So these models are very, very close to each other with this E in it. 38 months, we got 23.5. And 100 months later, we've got 66.5. So what's going on here? It looks very close, right? These models are very similar, but the model with E that represents continuous growth is always a little bit bigger, right? As we kind of go out in time. And as we go further out, it's a little bit even more. But it's very close, but it's just a little bit more because why? Because that compounding is happening more and more frequently. In fact, instantaneously. So the models produce similar results. But the one with E is always a little bit larger. Let's get fancy here. Okay. But these models are close, so if you wanted to represent this 2%, you could do it either way. And with or without E, or with E. So here's our continuous growth formula. Before we had a formula before for just regular exponential growth. We changed it a little bit for kind of like if we were growing incrementally, but in smaller intervals over time. And now we've got this continuous growth formula if you wanted to represent continuous instantaneous change. What does it look like? It looks like P, our principal, again, times E to the R times T. R is our growth rate. T is still our time. On the next screen, I want you to take a look comparing these two models, this model with the other model, for the same value of R, for the same rate. And are they always similar? Are there differences between them? I want you to take a look. If there are any differences, what are they? All right, let me pause the screen, and you do that. Go on to the next screen and play around with this model. Play around with this model here, kind of changing the value of R. We've got our original model, and we've got our model with E. Okay, so hopefully you took a break. Yeah, if you look at this, like what do you notice? So if R is 1%, right? Well, this is a 1% increase. I can't even tell the difference between the red and the green graph. They look so similar. What happens as this increases? So 2%, 3%, 4%. Each time we can see the green and the red graph are kind of next to each other. They're close to each other using both of these models. The green graph is always slightly more. And it's this limit of if we wanted it to increase by a certain percentage, say 5%, once each month or each time period, or continually continuously by breaking that down into infinitesimal kind of like increments, reaching this limit called E. Okay, so let's go ahead. So in summary, we've looked at 3 different models for exponential change, each with the same rate of growth. We've got our once per time period formula. We've got our n time periods formula happening n times. And we've got our continuous growth formula happening at every instant of time. Right? How do these compare to each other? Which one ends up giving us the slowest value? Which one gives us the largest, the fastest value? Why is there a difference? Think about that for a minute and write down some answer. All right, so let me come back to this. We kind of explore these different models, these different formulas. Each one model is close to the rest, right? They're all pretty close to each other in terms of like the values that they give. But the first, kind of the slowest growth, right? The slowest exponential changes. Once, say 2% a year or something like that. And the last model with E, fastest. It's not like super fast. It just increases a little bit because of the compounding more and more often. You could even say this is instantaneous. Of continuous compounding. So this is it doesn't, it's not a huge amount, but it is a small increase. Lastly, I want you to take a look at this cooldown. Suppose we wanted to model the population of a city in thousands of people, T years after 2010, using these 3 different models here. Describe how each model predicts the population of the city, or how the population grows in each model, and what each gives you as a prediction for 20 years later. I'm going to leave that up to you. Write your answers in, and I will leave you some feedback. If you didn't notice, I left you feedback on the last lesson, and I will do the same thing with this lesson by Friday. You can look at it Friday morning, go back in here, and you should be able to see on the right-hand side here some kind of notes from me. So go ahead, try to describe for yourself, how are these models different, and what are their different predictions. And then lastly, check, kind of cool down, reflect, tell me how this felt today, if the math made sense, if it was confusing, if this topic was interesting or not, and just how you're feeling. Let me know. I'm always interested to hear from you guys. I miss you. I'm a little still sad that I'm not going to get to see you before the end of the school year, but I hope that I see you again. All right, I'll talk to you guys later.